Hey guys, so today we're looking at Algebra 3's 3.4 Day 2 notes, so let's go ahead and get into it. Whoops. So, Day 2 it builds on the idea of being able to find zeros and behavior of polynomials by looking at different parts of the actual polynomial. And today we're looking at the fundamental theorem of algebra, which I think is an incredibly overrated, self-important theorem. You call it the fundamental theorem of algebra, and it turns out to be just like a bunch of crap. Sorry to any professors who think that the fundamental theorem of algebra is great and all. I just don't. It's so... I guess we'll get to it. Whatever. I should stop ranting. Then we'll talk about Descartes' rule of signs, which is so much more useful. Then we will find zeros of a polynomial on a graphing calculator. So, let's get to it. The fundamental theorem of algebra. I wouldn't even write this down if I were you. It is so... it is so pointless. It's like... it's so general. It's like... I don't even know. It's like a fortune teller telling you that you will get out of bed tomorrow morning. Like, what? Yeah, thanks. I already knew that, right? Like, the sun will rise tomorrow. Wow, how insightful. This theorem says that if f of x is a polynomial of degree n, where the degree is at least 1, so basically, if you have a polynomial that has a variable in it, then, jeez, it's so funny just to think about this stupid theorem. If your polynomial has a variable in it, then there is at least one complex root. Not even a real root. Just some complex root. I mean, the complex root could be a real root because, this is a complex number, right? That's a complex number, but this is technically also a complex number, which is just 3, right? So all this theorem says is that if you have any type of polynomial where there is something besides just a constant, you'll have at least one root, and the root may be complex. How incredibly insightful. Man, I get all fired up just thinking about this dumb theorem. And like the book basically just like salivates over it. There's like stars in the book. Like, what a great theorem. We can know there's at least something. Anyway, whatever. I'm not even going to get into it anymore. Oh wow, this polynomial. Oh my gosh, it has at least one complex root. What about a polynomial that has 50 terms in it? Oh, it has at least one root. Wow, worthless. Anyway, moving on. I just cover it because I have to cover it, all right? It's a thing I have to cover. And anyone who argues with me, like, really? Really? What use is it? Let's be practical here. So, next, Descartes' rule of signs. Now, this is a very helpful rule, and it doesn't even go so far as to call itself a theorem. It's just like a rule, all right? And that's not the most fundamental. He just put his name on it, which he has a right to. Descartes' a pretty smart dude. So, looking at the variations in sign between consecutive coefficients when the polynomial is in standard form, the number of sign changes tells you the maximum number of real zeros the polynomial can have. Oh my gosh, it's already so much more useful. So first off, it works for any polynomial. They don't just have to have integer coefficients, so we're already ahead of the game in terms of comparing it to the rational root theorem. Then you don't have to, all you have to do is think about the polynomial when it's in standard form, so you don't have to add anything and nothing like that. The number of sign changes tells you the maximum number of real zeros the polynomial can have. Man, This is so useful, and you will see. And we'll look right back at this polynomial here in just a second, okay? Now, the number of sign changes on the original function tells you how many positive real zeros could exist. The number of sign changes on f of negative x tells you how many negative real zeros could exist, or a maximum, right? The maximum and the maximum, because this tells you the maximum number. Now, let's go ahead and get into it. This is such a cool rule, in my opinion. It takes no work for you to do. There's no actual working it out. You just have to have the rule in your head, and then you can see it. So the idea here is make sure your polynomial is in standard form, which means it's in descending exponent order. So you've got a 3 and then a 2 and then a 1 and then a nothing, right? This is standard form. You don't want to write it backwards or anything like that. Now, you want to read it left to right and look at the signs of each term. So this is a positive x to the third, this is a negative, this is a negative, and this is a positive. So you have to think. You have to count to yourself, how many times did the sign change? The sign change. So it was positive, then it switched to becoming negative. That's one change. Then it became negative. It was still negative, so no change. And then from negative to positive, another change. So we have two changes. So there were two sign changes on f of x. That means there is a maximum of 2. That's what this rule says. That the number of sign changes tells you the maximum number of real zeros the polynomial can have. So the number of positive real zeros is 2. Now we have to consider the negative real zeros. Now to get the negative zeros, you'll have to look at f of negative x. And f of negative x we should be familiar with by looking at even and odd functions. So you plug in a negative x everywhere there's an x. Whoops, that was not a negative x. So simplify this, and you're going to have negative x to the third, and this is going to be so this part right here is going to be a positive x squared, so that's still going to be a negative 2x squared. Then this is going to multiply and give you a positive 5x, positive 4. And now you look at the number of sign changes. So negative, negative, there's a sign change. From a negative to a positive is a sign change. And then a positive to a positive, no more sign changes. So this has a maximum of 1 negative real zero because there was only one sign change. It went from negative to positive, no other changes. This is so much more useful because if you're having to match this to a graph, it's possibly faster just to look at using Descartes' rule of signs to tell you whether or not these different choices could be possibilities. Because if this polynomial was to match to a multiple choice section that had 3, so this has got, let's see, this has got 3 positive zeros. This could not be a choice, right? Like if it looked like this. Let's see here. How do I want to do this? There we go. That's a polynomial that fits based on the end behavior, a positive leading coefficient, even or odd degree polynomial that has 3 positive roots, zeros. So that means that this could not be a possibility because it has only a maximum of 2 positive real zeros. I think this is really cool. Now, let's look at this other polynomial here. We should know what x squared plus 4 looks like. It's just your regular quadratic that's moved up 4. Looks like this, right? Something like that? Well, how many sign changes are here? None. There are 0 sign changes, which means there's a maximum of 0 real roots. That's really helpful to us. Knowing that there's a maximum of 0 real roots, that means you can immediately stop looking for intercepts and start doing other more helpful things depending on what you're being asked. So, moving on. If there is, now this is also really cool. If there is only one sign change, then there is exactly one positive real zero. So this, not only does it tell you the maximum number, but if there is one sign change, then there will be one real zero. And if you're evaluating the sign changes at f of x, then that's positive zeros, and f of negative x would be negative zeros. Or negative, yeah, real zeros. So let's look at this. State the maximum number of positive and negative real zeros of the following polynomial. If you think you can tell me the maximum number of positive and negative real zeros of this, well, pause the video and go for it. And you see if you can do it. All right? The students who do this are going to have a much better time in this class than the students who don't. So if you have been historically not pausing the video, you are removing the part of the learning process that is so important. You need to practice doing things on your own and then get guidance if you fail. This is the whole point. That's how you learn. Right? So please, if you typically don't pause the videos, please do so and try to attempt to do it. Look back at the notes that you took and that kind of thing to try to figure it out. And if you get stumped, then resume the video. All right, I cannot say this enough. Now, so positive. So we're looking at the positive maximum real zeros here. Number of sign changes, no sign change. No sign change. There's a sign change. So we have one positive real zero. And since there's only one sign change, we can conclude that there is exactly one positive real zero. Man, that's so helpful. Next, we need to look at negative real zeros. In the negative real zeros, you must evaluate f of negative x. F of negative x. F of negative x. I'm not going to have enough space. I'm not going to have enough space. And that was such a good negative x. F of negative x. And now you simplify this, and you're going to get... So this piece right here, just the negative x to the third, is negative x to the third. And the negative times the negative make it a positive x to the third. Then you've got this will become a positive x squared, and then the negative 4 will still make it negative. Then this will become a positive 7x, and this is a positive 10. So we've got, count the sign changes, positive to negative, that's one change. Negative to positive, that's another change. And then positive to positive, that's not a change. So there's two changes. So you've got a maximum of two negative real zeros. So I might ask you like true or false questions, like what's the maximum number of negative real zeros this polynomial could have by using Descartes' rule of sign? And then I'd give you a list of choices. And you could have to tell me which one it is. So, and it could be true or false by saying, does the polynomial have exactly one positive zero or whatever, something like that. Now, here's how you use a graphing calculator to find the zeros of the polynomial. Now, I'm going to slowly scroll down here, and feel free to write this down if you would like. I will also work out an example in this video as soon as we get done scrolling through here. So you'll enter the polynomial into y equals, then you'll press graph, make sure your window is set to something reasonable. Then you'll set second trace, you'll go to the 0 option. When it asks for left bound, you'll move your cursor to the left of the 0 you're looking at, and then press enter. For right bound, you'll move the cursor to the right of the 0 and press enter. For guess, you will just press enter again, and the 0 should be listed at the bottom of the screen. So let's go ahead and do this. So turning on your calculator, you go to press y equals, then you enter in the polynomial. So 2x to the third, 2x to the third. Next, minus x squared, minus 9x, minus 4. All right. Then you press graph. Now, something to note. if you just briefly look at this polynomial, it's already in standard form, and there's only one sign change. That means that there's exactly one positive real zero, and it is right there. You can see it. Zeros, remember, are x-intercepts. So there's a zero right there. But there are two more right here. Right there and right there. There are two zeros. So I am going to use second trace, and I'm going to the zero feature, which is number 2. Now, here's the thing. You will need to do this for every zero that you're looking for. There are 3 zeros here, so we're going to need to do it for each one of them. It asks left bound. So you can see my cursor is right here. You see the little cursor? You can see that blinking right there. If I use the left and right arrows, it will move left and right following the graph. Now, something to point out. Ignore that the graph is going, that the cursor is going up and down. The important thing is that it's moving left and right. So when I press left, it traces the function going towards more left x values. So you want to move the cursor until it is on the left side of the zero I'm looking at. And this is the zero I'm wanting to find. This one little zero right here, that's the one I want to find. So I'm going to move my cursor to the left of it. I am officially to the left of this zero because I am at an x value that is farther to the left on a number line. And you can do that by just pressing left and right. Now you press enter. Then it asks for right bound, so you move the cursor to the right using the right arrows until you are on the right of the zero. So look, I passed over the zero, so I moved left, I'm on the other side of the zero. Move to the right, I'm on the other side of the zero. Remember, the zero is the x-intercept. So I know I'm on the right side of it now. So I press enter and then enter again. There's the zero, negative 1.561553. And so I'll write that down, negative 1.56-ish. Negative 1.56, comma 0. So there's one of the zeros. Now the second zero. Second trace, go down to 0. Now this time I want to find this one here, this little zero right there. So I want to make sure I'm on the left side of it, which I am now, because look, I'm on the left of it because it's to the right. Now I want to go to the right, press enter again, and now I press guess. Negative 0.5. This is not approximately, this is actually negative 0.5. So there's another zero. And then, actually, these are intercepts. These are intercepts. Zeros would be negative 1.56, the actual values, negative 0.5. I won't hold you to that. But the values are, I think, technically what we're looking for. And next, second trace, go to zeros. This time I want to find that one, so I'm already way to the left of it, so just consider that. And then I'm going to move. All right, there, I'm to the right of it now. You can see my cursor right there. And it's at 2.56-ish, so 2.56-ish. So those are my zeros. There's your homework, 34 through 37, 43, and 44. Hopefully this lesson was okay for you. If you have any questions, please let me know. And it's like 15 minutes shorter than your last lesson, which is good. So see you guys next time.